Understanding the temporal and geographical distribution of earthquakes. Ladies and gentlemen, today we are going to take a deep, holistic look at a topic that shapes landscapes, influences civilizations, and reminds us of the immense power resting beneath our feet, the temporal and geographical distribution of earthquakes. In other words, where do earthquakes happen, and when do they happen? And perhaps equally important, what patterns can we observe in these two dimensions? To truly appreciate these patterns, we need to begin with a quick reminder of what earthquakes fundamentally are. Earthquakes occur when accumulated stress in the Earth's crust is suddenly released, typically along fractures called faults. This stored energy radiates outward as seismic waves, shaking the surface. While this is a simple explanation, the distribution of earthquakes in time and space is anything but simple, yet it is wonderfully predictable in many respects. So let's begin with geographical distribution, the where of earthquakes, before transitioning into temporal distribution, the when. Along the way, we'll explore plate boundaries, seismic belts, intraplate regions, aftershock sequences, long-term recurrence intervals, and major global trends. 1. Geographical distribution. Where earthquakes occur. If you look at a global seismicity map, one that shows every recorded earthquake over several decades, you will notice something striking. Earthquakes are not randomly scattered across the earth. Far from it. They form distinct lines, arcs, and clusters that almost perfectly outline the boundaries of Earth's tectonic plates. More than 95% of the world's earthquakes occur along these plate boundaries. The patterns are so clear that early scientists used earthquake data to help confirm plate tectonics long before GPS existed. Let's break down the major seismic zones of the world and see what makes each unique. A. The Circum-Pacific Belt, the Ring of Fire. The most famous and active seismic zone in the world is the Circum-Pacific Belt, often known as the Ring of Fire. It encircles the Pacific Ocean like a fiery horseshoe, stretching from South America up through Central America, along the west coast of North America, across Alaska, through Japan, the Philippines, Indonesia, and then down to New Zealand. Roughly 75% of the world's earthquakes, and about 90% of the world's largest earthquakes, originate here. Why? Because the Pacific Plate and surrounding plates form long, complex subduction systems where one plate dives beneath another. Subduction zones are prime locations for intense pressure buildup, and when the locked zones finally rupture, the resulting earthquakes can be enormous. The 1960 Chile earthquake, the 2011 Tohoku earthquake in Japan, and the 2004 Sumatra-Andaman earthquake, all originated in subduction zones along this belt. These regions also produce devastating tsunamis, since vertical displacement of the sea floor is common in subduction events. So the Ring of Fire is not just active, it is hyperactive. B. The Alpide Belt, the Mediterranean Himalayan Seismic Zone. The second major seismic zone is the Alpide Belt, which stretches from the Mediterranean region across southern Europe, through Turkey, Iran, the Himalayas, and into Southeast Asia. This zone exists because of the slow but relentless collision of the African plate and the Indo-Australian plate with the Eurasian plate. The collision produces immense compressive forces, crumpling land upward to form mountain chains like the Alps, the Zagros Mountains, and, most dramatically, the Himalayas. Earthquakes here tend to be shallow to intermediate in depth and can be extremely deadly, not only because of the high population densities but also because many affected regions have vulnerable infrastructure. Historical examples include the 1999 earthquake in Turkey and the 2015 Nepal earthquake. Although not as seismically active as the Ring of Fire, the Alpide Belt accounts for about 15% of global earthquakes and includes some of the most destructive in human history. C. Mid-ocean ridges. Next, we turn to the mid-ocean ridge system, a global chain of submarine mountains where tectonic plates are pulling apart. Here, we see earthquakes that are typically shallow, frequent, but relatively small in magnitude. Examples include the Mid-Atlantic Ridge, the East Pacific Rise, the Indian Ocean ridge systems. Because these earthquakes occur under deep ocean waters and involve relatively low energy releases compared to subduction zones, they rarely cause damage or pose significant hazards to humans. Nonetheless, they represent a crucial component of the Earth's seismicity and help maintain the continuous creation of new oceanic crust. D. Intraplate regions, earthquakes away from plate boundaries. Although most earthquakes occur at plate boundaries, a small but important minority happen within the interior of plates, far from plate edges. These are called intraplate earthquakes. Examples include the New Madrid seismic zone in the central United States, the Charleston area of South Carolina, the Delhi and Kutch regions in India, Australia's interior faults, parts of eastern Canada and China. Intraplate earthquakes are often the result of ancient fault lines reactivating due to regional stress fields. Although they are less frequent, they can be surprisingly powerful and destructive. Because populations in intraplate zones tend to be less prepared for earthquakes, even moderate events can have severe consequences. E. Earthquakes associated with human activity, induced seismicity. Although not traditionally part of natural geographical distribution, the last few decades have seen a rise in induced seismicity, including earthquakes linked to reservoir impoundment behind large dams, hydraulic fracturing, fracking operations, wastewater injection deep underground, large-scale mining or geothermal operations. These earthquakes are typically small, but certain regions, particularly parts of Oklahoma in the United States, have experienced swarms of induced earthquakes large enough to be felt widely. This phenomenon illustrates that while natural plate processes dominate seismicity, human activity can influence stress conditions enough to trigger earthquakes in susceptible regions. 2. Temporal distribution. When earthquakes occur. Now that we've established where earthquakes are most likely to occur, let's consider the other half of the puzzle: when, or how earthquakes are distributed through time. When analyzing temporal distribution, we consider several timescales. Seconds to minutes, aftershocks. Days to years, seismic swarms, stress triggering. Decades to centuries, recurrence intervals on major faults. Millennia to millions of years, long-term plate motion patterns. Let's explore each of these layers. A. Earthquakes do not follow predictable short-term patterns. First, it's crucial to state that scientists cannot reliably predict the exact time of an earthquake. Earthquakes do not follow a regular daily, monthly, or yearly pattern. While there are tectonic forces constantly at work beneath the Earth, the transition from stress accumulation to sudden rupture is far too complex and sensitive to predict with current science. Patterns do exist, but not in the sense of precise timing. Instead, we rely on long-term statistical probabilities and recurrence intervals, which we'll discuss shortly. B. Aftershock sequences. The most predictable temporal pattern. Although predicting the main shock remains beyond scientific reach, the behavior of earthquakes after a major event is much more predictable. After a large earthquake, the crust around the rupture zone is left in a highly stressed and readjusting state. This leads to aftershocks, which follow well-established empirical laws. Omori's law. Aftershock frequency decays roughly in a hyperbolic pattern, many aftershocks immediately after the main shock, gradually decreasing over days, weeks, and months. Productivity law. Larger earthquakes produce more aftershocks, and they tend to last longer. Bart's law. The largest aftershock is typically about 1 magnitude unit smaller than the main shock. These patterns don't tell us exact times, but they tell us what to expect statistically. C. Foreshocks. Sometimes helpful, mostly unreliable. Foreshocks. Smaller earthquakes preceding a larger event offer tantalizing clues but are unreliable for prediction. Not all major earthquakes have foreshocks, and many small quakes that look like foreshocks never lead to anything. In some rare cases, foreshock sequences have alerted scientists and agencies to heightened risk, but they are not consistent enough to serve as forecasting tools. D. Earthquake swarms. Instead of a single main shock with aftershocks, some regions experience swarms, where many small to moderate earthquakes occur over days or weeks without a single dominant event. These occur in volcanic areas, geothermal fields, and regions of complex crustal stress. Swarms do not follow typical aftershock decay patterns and can be mistaken for precursors to larger events, though they often dissipate without major consequences. E. Long-term recurrence intervals. Probabilistic rather than predictive. On the scale of decades to centuries, earthquakes show clearer long-term patterns based on fault mechanics. Most major faults exhibit recurrence intervals, meaning they tend to produce large earthquakes at roughly regular long-term intervals. For example, the San Andreas Fault in California has segments that rupture every 150 to 200 years on average. The Cascadia subduction zone in the Pacific Northwest shows evidence of megathrust earthquakes roughly every 300 to 600 years. The North Anatolian Fault in Turkey shows a remarkable sequential westward progression of major earthquakes over the 20th century. These intervals are based on long-term averages, not precise cycles. A fault with a 200-year recurrence interval might rupture after 150 years or after 350 years, depending on stress interactions with nearby faults. Thus, recurrence intervals inform probabilistic forecasting, such as, there is a 30% probability of a magnitude 7 earthquake in this region in the next 30 years, rather than precise predictions. F. Seasonal and tidal influences. Minor but observable. Some studies have shown weak correlations between seismicity and large seasonal snow loads, groundwater variations, ocean tidal forces. However, these effects are subtle and small compared to tectonic stresses. They do not significantly influence major earthquakes but may slightly modulate the timing of small ones. G. Temporal clustering across centuries. When we zoom out to millennia or millions of years, the temporal distribution of earthquakes reflects the slow choreography of plate tectonics. Earthquake activity increases or decreases along certain boundaries depending on changes in plate motion rates, evolution of subduction zones, formation or closure of ocean basins, continental collisions and rifting events. On geological timescales, entire seismic belts can rise and fall in activity as the architecture of plates changes. 3. Bringing it together. Why these patterns matter. Understanding the geographical and temporal distribution of earthquakes is not only a scientific pursuit, it's essential for societies living in seismic regions. The patterns we've discussed help engineers, planners, governments, and communities make informed decisions about building codes, disaster preparedness, and risk assessment. For example, California's strict building codes are shaped by its position on the San Andreas system and its statistical recurrence rates. Japan's advanced early warning systems stem from its location in the Ring of Fire. Turkey's urban planning efforts and Istanbul's retrofitting initiatives are informed by the North Anatolian Fault's seismic history. Megacities on intraplate faults, like Delhi, must prepare for rare but severe earthquakes in regions where awareness may be limited. Although we cannot predict the exact timing of earthquakes, understanding where they occur most often, and recognizing long-term recurrence patterns, allows us to reduce risk dramatically. 4. Conclusion. To summarize, the geographical distribution of earthquakes is dominated by the architecture of Earth's tectonic plates. The Ring of Fire and the Alpide Belt are the world's most active regions, with mid-ocean ridges and intraplate zones contributing smaller but still significant portions of global seismicity. These patterns align closely with plate boundaries and the dynamic interactions between them. In terms of temporal distribution, earthquakes show a rich variety of patterns across different timescales. Short-term variations such as aftershock sequences and swarms follow well-established behaviors, while long-term recurrence intervals provide probabilistic, but not deterministic, timelines for major events. Across centuries and millennia, seismic activity shifts in concert with plate tectonics. Ultimately, earthquakes remind us that our planet is alive, restless, dynamic, and constantly evolving. By understanding the patterns through which they occur, we gain not only scientific insight but practical tools for protecting lives and communities. Seismicity and seismotectonics of India and the Himalayas. When we talk about the seismicity and seismotectonics of India and the Himalayas, we are really talking about one of the most dynamic, powerful, and geologically vibrant regions on Earth. Few places on the planet offer such a dramatic example of continents colliding, mountains rising, crust deforming, and energy building up in the Earth's interior. This process didn't begin recently, nor is it anywhere near finished. It is a slow, relentless tectonic interaction between two enormous lithospheric plates, the Indian plate and the Eurasian plate. And it is this interaction that gives rise to the towering Himalayas, the high Tibetan Plateau, and the significant seismic hazards across much of northern India. So let's begin by placing everything in context, starting with the broad tectonic framework. 1. The tectonic setting, India on the move. The Indian plate was once part of the ancient southern supercontinent Gondwana. Roughly 130 to 140 million years ago, it began drifting northwards, breaking away and racing toward Eurasia at an unusually rapid geological speed. Estimates suggest up to 15 to 20 centimeters per year at certain times. Today, the plate still moves northward at about 4 to 5 centimeters per year. This may sound small, but in geological terms it's fast, and the consequences of this motion are immense. Around 50 million years ago, the Indian plate collided with the Eurasian plate. Instead of India simply subducting neatly beneath Eurasia, as oceanic plates usually do, this was a collision between two continental masses, both buoyant, both resistant to sinking. The result was massive crustal thickening, folding, and faulting, and ultimately the formation of the Himalayan mountain belt and the uplift of the Tibetan plateau. This ongoing collision is the engine behind almost all of northern India's earthquakes. The energy generated by this convergence accumulates in the crust, and when stresses exceed the strength of rocks along faults, earthquakes occur. 2. The Himalayan arc, a giant compressional system. Now, if you look at the Himalayas from above, they form a graceful yet massive arc stretching across about 2,400 kilometers. This arc is not a simple, uniform belt. Instead, it is made up of several distinct tectonic elements and fault systems. The three major thrust faults that define the Himalayan tectonic architecture are the main frontal thrust, MFT, the main boundary thrust, MBT, the main central thrust, MCT. These faults represent different levels of deformation within the Himalayas, from the most recent and shallow deformation in the south to older and deeper structures toward the north. The main frontal thrust, located near the foothills, is currently the most active and accommodates a major portion of crustal shortening. North of it lies the main boundary thrust, associated with older but still active deformation. Farther north is the main central thrust, representing deeper crustal folding and metamorphism. Together, these structures form the backbone of Himalayan seismotectonics. They are responsible for many of the large, devastating earthquakes in history. 3. Historical and modern seismicity in the Himalayas. The Himalayas have experienced a long and tragic record of destructive earthquakes. Let's highlight a few important ones because each offers insight into the seismotectonic processes at work. The 1897 Shillong Plateau earthquake, MW approximately 8.1. This event is unusual because it did not occur on the main Himalayan thrusts but within the Shillong Plateau, which accommodates some of the convergence between India and Eurasia. It involved a massive rupture of a basement-involved fault, demonstrating that the region is more complex than a simple linear belt. The 1905 Kangra earthquake, MW approximately 7.8. One of the classic Himalaya thrust earthquakes, causing widespread devastation in the Kangra Valley. The 1934 Bihar Nepal earthquake, MW approximately 8.1. One of the largest Himalayan earthquakes ever recorded, rupturing a long segment of the main frontal thrust. The 1950 Assam earthquake, MW approximately 8.6. One of the largest continental earthquakes in the world. Unlike typical Himalayan thrust earthquakes, this one likely involved complex faulting near the eastern Himalayas and the Indo-Burma ranges. The 2005 Muzaffarabad earthquake, MW 7.6. A catastrophic event in the Kashmir region, highlighting active thrust and oblique slip faulting in the western arc. The 2015 Gorkha, Nepal, earthquake, MW 7.8. This earthquake ruptured a mid-segment of the main Himalayan thrust but left the frontal portions unruptured, suggesting stored strain remains high. These events show a critical truth. The Himalayan arc has not released all its built-up stress through frequent moderate earthquakes but instead tends toward infrequent, very large earthquakes. This makes it one of the most hazardous seismic belts on Earth. 4. Seismotectonics of the Himalayas. Strain accumulation and release. To understand Himalayan seismotectonics, imagine the Indian plate as a rigid block pushing northward. The Eurasian plate resists this motion. The rocks in between deform, fold, and fracture, storing elastic strain. The main Himalayan thrust, a master decalment running from the surface down to depths of 30 to 40 kilometers, is the primary plane along which the strain accumulates. GPS measurements conducted across the Himalayas show that India's northward motion is partially locked at the surface. The plates may be slipping at depth, but the shallow parts of the main Himalayan thrust are stuck. This is like pushing two rough surfaces together. At depth, heat and pressure allow some sliding, but at shallower depths, friction locks them in place. Eventually, the strain is released catastrophically as an earthquake. Thus, the Himalayas behave as a megathrust system, comparable in some ways to the subduction zones of Japan, Chile, or Alaska. 5. Segmentation of the Himalayan arc. Despite being one continuous mountain chain, the Himalayas do not rupture all at once. Instead, they are divided into seismic segments, zones that tend to break independently. Some of these segments have ruptured in the past century, others have not ruptured for hundreds of years. For instance, the Kumaon Garhwal segment has not seen a great earthquake since possibly the 1505 event. The Central Himalaya segment saw the 1934 and 2015 events but still retains unruptured portions. Parts of the Assam segment ruptured in 1950, but stresses remain unevenly distributed. This segmentation means that although one part ruptures, others remain highly stressed. That is why seismic hazard models repeatedly warn of the potential for future great earthquakes, MW8 or greater, in several Himalayan segments. 6. Seismotectonics beyond the Himalayas. The Indian Shield and intraplate earthquakes. While the Himalayas dominate the seismic narrative, the rest of India is far from a seismic. The Indian peninsula, often described as a stable continental region, actually hosts several significant seismotectonic provinces. Three major types of earthquakes occur south of the Himalayas. Stable continental region earthquakes, such as in Latur, 1993, Koyna, 1967, and Jabalpur, 1997. Intraplate earthquakes related to reactivation of ancient faults. Reservoir-triggered seismicity, especially notable around the Koyna-Varna region. Let's take each in turn. A. Peninsular India. Peninsular India is dissected by ancient Precambrian and Proterozoic lineaments, faults, shear zones, and rift systems that originated long before the Himalayas existed. Tectonic stresses from the Himalayan collision propagate deep into the plate interior, reactivating these ancient structures. This is why the 1993 Latur earthquake, which struck a region thought to be extremely stable, took scientists by surprise. Koyna, in Maharashtra, remains one of the most seismically active intraplate regions globally. Many studies link its seismicity to reservoir loading and unloading cycles, making it a classic site for studying reservoir-induced seismicity. B. The Shillong Plateau in Northeast India. Northeast India is one of the most complex seismotectonic regions in the world. It is squeezed between the Himalayas to the north, the Indo-Burma ranges to the east, and the Indian Shield to the south. This area experiences frequent moderate to large earthquakes and has hosted mega events such as the 1897 Shillong and 1950 Assam earthquakes. The region's tectonics involve the Eurasian-Indian collision, the subduction of the Indian plate beneath the Burma plate, the interaction with the Tibetan plateau, and strike slip and thrust faulting within the Shillong plateau. The Indo-Burma region is essentially an oblique subduction zone, which contributes to significant seismic activity. 7. Seismicity of the Indo-Gangetic Plain. Interestingly, the Foreland Basin, the plains south of the Himalayas, also experiences earthquakes. These are typically moderate in magnitude but occur because stress from the Himalayan collision propagates southward. The basin is underlain by a network of hidden faults, many of them blind thrusts, such as the Mahendragarh-Dehradun fault, the Faizabad fault, and the Delhi-Haridwar ridge system. The 1803 and 1720 Delhi earthquakes demonstrate that regions far from the main Himalayan front can still experience damaging earthquakes. 8. Why earthquakes in India can be so destructive. Several factors contribute to the high vulnerability of the Indian subcontinent. High population density in earthquake-prone regions, especially in the Indo-Gangetic plains. Soft sedimentary basins that amplify seismic waves, causing prolonged shaking. A large stock of non-engineered buildings, which perform poorly during earthquakes. Steep Himalayan terrain, which is prone to landslides triggered by shaking. Secondary hazards, including liquefaction in alluvial plains and glacial lake outburst floods, GLOFs, in the Himalayan region. 9. Seismotectonic framework, putting it all together. To summarize the seismotectonic architecture, the Indian plate continues to push northward. The main Himalayan thrust accommodates most of the convergence, storing enormous strain. This strain is episodically released in great earthquakes that rupture entire segments of the thrust system. Above this thrust, a set of major splays, MCT, MBT, and MFT, define the Himalayan structure. The Himalayan arc is segmented, leading to uneven distribution of seismic hazards. Intraplate regions within India experience occasional earthquakes due to reactivation of ancient faults and stresses transmitted from the collision zone. Northeast India is an independent but related seismotectonic province with complex plate interactions involving Indian, Eurasian, and Burmese plates. 10. The future, seismic hazard and preparedness. Modern GPS, INSAR, and seismological studies consistently show that many Himalayan segments remain locked. Strain accumulation rates are high. Several regions are overdue for major earthquakes. This doesn't mean earthquakes can be predicted with exact timing. Earthquake prediction remains beyond scientific reach, but it does mean that significant seismic risk remains. Geologists estimate that parts of the Himalayas could still produce earthquakes of magnitude 8 or higher. For example, the central Himalaya between Kathmandu and Dehradun is considered capable of a great event. The Kumaon-Garhwal segment has not ruptured for centuries and is seen as highly stressed. The eastern Himalaya remains seismically active and complex. The challenge now is not just understanding the tectonics but translating this understanding into earthquake-resistant infrastructure, public awareness, seismic zoning, and disaster preparedness. 11. Closing thoughts. In conclusion, the seismicity and seismotectonics of India and the Himalayas represent one of the most fascinating geological stories on Earth, a story of continents colliding, mountains rising, crust deforming, and energy building up over millions of years. But it is also a story with profound human implications. The same tectonic forces that created the world's highest mountains also generate some of the most powerful earthquakes known. Understanding these processes allows scientists, engineers, and policymakers to better assess hazards and work towards safer communities. And although we cannot stop the Indian plate from moving, we can certainly learn to live more safely on this dynamic planet. Indian earthquakes, historical perspective. When we talk about earthquakes in the Indian subcontinent, we are really talking about a story that began tens of millions of years ago, a story of drifting continents, colliding landmasses, and the tremendous geological forces that continue to shape this region even today. To understand why India experiences so many damaging earthquakes, and why some parts of the country are especially vulnerable, we have to go back to the deep past, long before humans settled here, long before the Himalayas stood as the roof of the world. The tectonic background, how India became earthquake prone. Imagine the Indian subcontinent around 120 million years ago. Instead of being attached to Asia, India was part of a giant southern supercontinent known as Gondwana, which also included Africa, Australia, and Antarctica. Around 100 million years ago, the Indian plate began drifting northward, remarkably fast in geological terms, at about 15 to 20 centimeters per year. That's roughly the speed at which your fingernails grow, but for a chunk of crust thousands of kilometers across, this is practically racing. About 50 million years ago, the Indian plate slammed into the Eurasian plate. And this collision has been going on ever since. As India continues to push north, the land has nowhere to go but upward, giving birth to the Himalayan mountains and the vast Tibetan plateau. But this process isn't peaceful. The grinding, compressing, and bending of the Earth's crust releases enormous energy from time to time, and that energy comes out as earthquakes. This is why the Himalayas are one of the most earthquake-prone regions in the world. But earthquakes in India don't just happen in the mountains. The deep geological scars created by the breakup of Gondwana and the later northward journey of the Indian plate left behind weak zones running through central, western, and northeastern India. One of the most important of these is the peninsular shield, which for a long time was thought to be stable and safe. But as we'll see, several devastating earthquakes have come from these so-called stable regions as well. So with that geological background in mind, let's walk through the history of Indian earthquakes as recorded in chronicles, oral traditions, early administrative records, and modern seismology. Ancient and medieval period. Earthquakes in early records. India has a long history, and many ancient texts mention natural disasters, including earthquakes. Because early records are descriptive rather than scientific, many events are difficult to date precisely. But they give us a sense of how common earthquakes have been. For example, some texts from around 326 BCE, when Alexander the Great marched into northwestern India, talk about tremors in the Hindu Kush region. Sanskrit texts and Puranic literature also mention ground shaking, sometimes interpreted as divine signs or omens. Though these accounts are not precise enough for scientific study, they show that northern India, especially the Himalayan belt, has been active for millennia. By the medieval period, accounts grow more detailed. Persian and Indo-Islamic chronicles from the Delhi Sultanate and Mughal period describe earthquakes in North India, especially around Kashmir, Lahore, and the Gangetic Plains. For example, in 1548, Kashmir experienced a major quake that caused severe landslides. In 1737, a destructive event struck Bengal. Although historical records are unclear, it is thought to have affected Kolkata significantly. Still, Systematic data starts only in the 19th century with British colonial administration. Modern historical earthquakes, 1800s 1900s. Now let's move into the era when earthquakes were more thoroughly documented and understood. Several major earthquakes during this period shaped scientific understanding and public awareness. 1. The 1819 run of Kutch earthquake. This earthquake, around magnitude 7.7, dramatically reshaped the landscape. One of the most striking features it created was the Allah Band, a raised ridge nearly 6 meters high and 90 kilometers long. Imagine the earth lifting a long strip of land almost overnight. That's how powerful the forces beneath the surface can be. This event also showed scientists that the supposedly stable western part of India could produce very large earthquakes. 2. The 1897 Assam, Shillong Plateau earthquake. One of the largest continental earthquakes in history, estimated magnitude 8.1, struck the northeastern region, causing widespread destruction. It devastated Shillong, Sylhet, and surrounding areas. This earthquake is particularly important in seismology because it helped scientists understand the concept of intraplate earthquakes, where huge amounts of strain build up inside a plate, not just at its boundaries. The shaking was so intense that the Earth's surface shifted by several meters in some places. Roads opened up, hillsides collapsed, and buildings crumbled across the region. The 20th century, some of India's most devastating earthquakes. The 20th century saw several catastrophic earthquakes that shaped India's disaster planning and scientific efforts. 1. The 1905 Kangra earthquake. Striking Himachal Pradesh with a magnitude of about 7.8, the Kangra earthquake killed over 20,000 people. Entire villages were wiped out, especially in the Kangra valley. This quake reminded scientists that the Himalayan region stores enormous tectonic energy. Large sections of the fault ruptured, but the entire region did not release its pressure. This means that the potential for future large earthquakes still remains, something that modern seismology continues to emphasize. 2. The 1934 Bihar-Nepal earthquake. One of the most destructive quakes in the history of the subcontinent, this magnitude 8.0 earthquake devastated large parts of Bihar and Nepal. Cities like Muzaffarpur, Munger, and Darbhanga suffered massive destruction. In Nepal, Kathmandu Valley's historic architecture took heavy damage. What made the 1934 quake particularly notable was the liquefaction, the process in which water-saturated soil temporarily behaves like a liquid. Buildings sank straight into the earth. Farmers reported that water and sand erupted from their fields. This event is still studied today because it provides an important warning for the region. A similar earthquake could once again liquefy the soft sediments of the Gangetic Plains. 3. The 1950 Assam-Tibet earthquake. This magnitude 8.6 earthquake, one of the strongest ever instrumentally recorded on Earth, struck the Assam-Arunachal border region. Though the epicenter was in Tibet, the impact in India was enormous. Massive landslides blocked rivers, creating temporary dams that later burst, causing floods. This earthquake also demonstrated something crucial. The Himalayas are still very young, still rising, and still adjusting to the colossal forces beneath them. As long as the Indian plate continues to push into Asia, the region will continue to experience major earthquakes. Late 20th, early 21st century earthquakes. As India moved into the modern era, large earthquakes continued to occur, some in familiar zones, others where scientists least expected them. 1. The 1991 Uttarkashi and 1999 Chamoli earthquakes. These two earthquakes, magnitude 6.8 and 6.6 respectively, hit the Garhwal Himalaya. They were deadly but not massive compared to earlier Himalayan events. Still, they served as reminders that the central Himalayas are extremely active and overdue for a larger quake. The region between Uttarkashi and Nepal is considered one of the most hazardous seismic gaps in the Himalayas today. 2. The 1993 Latur earthquake. This was a shock, literally and figuratively. A magnitude 6.3 quake devastated Latur and Osmanabad in Maharashtra, killing around 10,000 people. What made it so surprising is that this region is in the interior of the Indian peninsula, far from tectonic plate boundaries. Scientists traced it to ancient fault lines reactivated by accumulating strain. It shattered the myth that peninsular India is earthquake safe. 3. The 2001 Bhuj earthquake. Perhaps the most devastating earthquake in recent Indian memory, the Bhuj earthquake in Gujarat measured magnitude 7.7. It killed over 20,000 people and flattened entire towns. The damage was widespread because the quake struck near populated areas and because buildings were not designed to withstand such shaking. Bhuj highlighted two major lessons. Large earthquakes can occur in western India far from plate boundaries. Building codes and planning are crucial for saving lives. 4. The 2004 Indian Ocean earthquake and tsunami. While the epicenter was near Sumatra, the magnitude 9.1 earthquake triggered a tsunami that hit India's east coast, especially Tamil Nadu, Andhra Pradesh, and the Andaman and Nicobar Islands. Over 10,000 people died in India alone. This was a global wake-up call. It led to the creation of tsunami warning systems and better coastal preparedness. 5. The 2015 Nepal earthquake. Again, though the epicenter was in Nepal, the Himalayan connection means India felt its impact strongly. Cities like Delhi, Patna, and Siliguri shook violently. This earthquake reminded the region that the central Himalayas are one of the most dangerous seismic zones on Earth. What makes India so seismically complex? There's no single cause behind earthquakes in India. Instead, it's a combination of tectonic processes. Continental collision. The India-Eurasia collision drives huge Himalayan quakes. Intraplate faults. Ancient faults within the Indian shield can reactivate. Subduction processes. In the northeast, the Indian plate sinks beneath the Burma microplate. Transform faults and rift zones. Western and central parts of India contain rift systems, such as the Narmada Sun fault zone. Because of this complexity, India is divided into four main seismic zones: 2, 3, IV, and V, with Zone V being the most hazardous. This includes Kashmir, parts of Uttarakhand, northeastern states, and the Run of Kutch. The current perspective. What the past tells us about the future. Looking at history, both ancient and modern, scientists can make some important observations. The Himalayas have had several very large earthquakes, but there are still seismic gaps that have not ruptured in centuries. These gaps are capable of generating earthquakes larger than magnitude 8. The central Himalayan region, stretching roughly from Himachal Pradesh to western Nepal, is particularly overdue. Intraplate earthquakes like Latur or Bhuj cannot be ignored. They may not occur often, but when they do, they can be devastating because communities do not expect them. Urbanization has increased dramatically. Cities like Delhi, Guwahati, Dehradun, Srinagar, and Gangtok are in or near high-risk zones. In many regions, buildings do not follow earthquake-resistant design, making them highly vulnerable. The story of Indian earthquakes is therefore not just a geological story. It's a story about preparedness, engineering, urban planning, and how societies learn from the past. Conclusion: a living, moving landscape. India is a land shaped by constant motion, tectonic motion that began millions of years ago and continues today. The earthquakes that we've seen through history, from the 1819 Kutch earthquake to the 2001 Bhuj disaster, from the deadly shocks in the Himalayas to surprising events in peninsular India, all point to the same conclusion: the subcontinent is dynamic and seismically active. Understanding this long history helps us prepare for the future. Earthquakes cannot be prevented, but history teaches us how to reduce their impact, through better buildings, thoughtful planning, early warning systems, and informed communities. The earth beneath India is still moving. And as long as the Indian plate keeps pushing northward, at about 5 centimeters per year today, the potential for earthquakes will remain. This isn't a cause for fear, but for awareness. Because the better we understand the past, the better we can protect ourselves in the future. Earthquakes, tsunamis, their devastation, and run up. Imagine the Earth not as a perfectly solid, unmoving sphere, but as a living, shifting planet made up of massive slabs of rock called tectonic plates. These plates are constantly moving, slowly, sometimes only a few centimeters a year, but irresistibly, always pressing, pulling, or grinding against each other. Most of the time, this movement is so gradual that we never feel it. But sometimes the plates get stuck. They lock in place even though enormous pressure continues to build at their boundaries. And when that pressure becomes too great, the rocks suddenly break, releasing energy in a violent burst. That sudden release is what we experience as an earthquake. Now, the shaking of the ground is only one part of what makes an earthquake so impactful. The deeper consequences, on buildings, infrastructure, people, and even the landscape, are what truly define an earthquake's destructive power. When the ground shakes, especially near populated areas, buildings can collapse, bridges can twist and snap, and roads can crumble. Utilities such as water lines, power grids, gas pipes, and communication systems rupture, sometimes causing fires or prolonged outages. The shaking destabilizes hillsides and mountains, triggering landslides that bury homes and roads. In cities, falling debris poses immediate danger, while in rural areas, even the ground itself can split, uplift, or sink. But some earthquakes carry an even greater risk, especially those that occur beneath the ocean floor. When a powerful earthquake happens underwater, the sudden vertical movement of the seabed displaces a massive volume of water. This displacement sends waves radiating outward across the ocean. These waves are not the familiar surface waves we see at the beach. Instead, they are long wavelength, high energy waves that can travel hundreds of kilometers per hour across deep water. And while they may pass unnoticed in the open ocean, sometimes only a few centimeters tall, they transform dramatically as they reach shallow coastal waters. These are tsunamis, some of the most devastating natural hazards on Earth. To understand why tsunamis are so destructive, picture a wave that is not just at the surface but extends from the ocean floor to the top of the sea. As that enormous wave approaches the shore, the shallower seabed slows the bottom of the wave while the upper part keeps moving quickly. This causes the wave to grow dramatically in height. What was once a gentle swell in the deep ocean becomes a towering wall of water near the coast, sometimes 10, 20, or even over 30 meters high, high enough to engulf buildings, forests, and entire towns. And it's not just one wave. Tsunamis often come in a series, with the first wave not always being the largest. The danger can last for hours. When a tsunami crashes onto land, the effects are catastrophic. The immense force of the water uproots trees, sweeps away vehicles, topples houses, and carries debris inland. The rushing water can erode the ground beneath buildings, undermining their foundations and causing them to collapse. Infrastructure, bridges, power stations, seawalls, water facilities, can be destroyed in moments. And because the water returns to the ocean after flooding inland, it drags debris, people, and entire structures back out to sea. This combination of incoming force and returning suction makes tsunamis uniquely dangerous. One of the most important concepts in describing tsunamis is run-up. The run-up is the maximum height above sea level that the tsunami water reaches as it travels inland. Think of it as the highest watermark left behind. Run-up helps scientists understand how powerful a tsunami was and helps communities plan safer building zones. A tsunami with a higher run-up means the water reached farther inland and climbed higher slopes, indicating greater destructive potential. In some extreme cases, run-up heights have exceeded 40 meters, taller than a 10-story building. But run-up doesn't just depend on the size of the tsunami wave itself. The shape of the coastline, the slope of the shoreline, underwater features, and even the layout of towns can affect how high and far the water travels. Narrow bays can funnel water inward, amplifying the wave's height. Shallow slopes allow the wave to push farther inland, while steep cliffs can force water upward, increasing run-up heights dramatically. Understanding these details is essential for preparing accurate evacuation routes and safe zones. The human and environmental impacts of earthquakes and tsunamis extend far beyond the initial moment of shaking or flooding. For communities struck by an earthquake, recovery is often slow and challenging. Homes may be uninhabitable, forcing families to live in temporary shelters. Businesses may close for weeks or months, disrupting livelihoods. Schools, hospitals, and government buildings might be damaged, limiting essential services. Roads blocked by debris or broken pavement can hinder rescue efforts. After large earthquakes, entire neighborhoods might need to be rebuilt from the ground up. In addition to physical damage, earthquakes can have psychological impacts. Experiencing the violent shaking, hearing buildings crack or crumble, or losing loved ones can leave lasting emotional scars. Survivors may feel anxious about aftershocks, which can continue for days, weeks, or even months. These aftershocks, although usually smaller than the main quake, can still cause weakened structures to collapse. For communities struck by a tsunami, the devastation is often even more widespread. Floodwaters contaminate drinking water supplies with salt water, sewage, and debris. Farmland may be rendered unusable due to salt deposits left behind by the ocean. Fishing industries can collapse if boats, ports, and equipment are destroyed. Critical infrastructure such as power plants or water treatment facilities may be severely damaged. Entire coastal towns may be left unrecognizable. Environmental impacts are also significant. Saltwater inundation can kill vegetation, disrupt ecosystems, and harm wildlife. Coral reefs, natural barriers that help reduce wave energy, can be shattered by the force of the tsunami. Wetlands and mangroves, which serve as important buffers against storms and waves, may be eroded or buried. And because tsunamis sweep debris far inland and back out to sea, the ocean and shoreline can become littered with hazardous materials. Despite the destructive power of earthquakes and tsunamis, knowledge and preparedness can dramatically reduce their impact. Early detection systems, such as seismic sensors and ocean buoys, can help identify tsunamis minutes after an undersea earthquake occurs. Although warning times may vary depending on distance, even a few minutes can make the difference between life and death. In regions prone to tsunamis, communities practice regular evacuation drills, identifying safe zones on higher ground and ensuring that residents know the fastest routes to reach them. Buildings are increasingly designed to withstand seismic forces through reinforced structures and flexible foundations. Still, even with preparation, the forces of nature can be overwhelming. Earthquakes and tsunamis remind us of the dynamic planet we live on, one that constantly reshapes itself through processes that have been occurring for millions of years. They remind us of our vulnerability and the importance of resilient communities, strong infrastructure, and well-planned emergency responses. In the end, understanding earthquakes and tsunamis is not just about geology or physics. It is about understanding risk, preparing for the unexpected, and respecting the natural forces that have shaped, and will continue to shape, our world. Through science, awareness, and thoughtful planning, we can reduce the devastation these events cause. But we must always remain alert, because while earthquakes and tsunamis may be infrequent, their impacts can be swift, powerful, and unforgettable.